Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 5, we will discuss about large-scale gasifiers. As you are aware that from the Module 4, we are discussing primarily about the gasifiers and we discussed about household gasifier stoves and the commercial gasifier stoves. Now we'll discuss the industrial scale gasifiers. To begin with, we'll discuss primarily about the biomass characterization so that we can understand what kind of properties are required. In this week, the different topics that we'll cover will largely focus on the commercial gasifier. However, to understand what kind of feed is suitable for commercial gasifier, we have to understand the biomass characterization. So we'll begin with the biomass characterization and then we will gradually move towards the large scale industrial gasifier and their theory. We'll also discuss how to develop the process flow diagram for the gasification plant of commercial scale. Like we have already discussed for the household gasifier stove, now we'll discuss the PFD of the gasification plant for commercial scale applications. We'll also discuss about the gasifier operating and design parameters, the gasifier classification and design, and different types of commercial gasifier which are manufactured and fabricated worldwide, and the major working principle as well as the major differences in this kind of gasifiers. We'll also discuss some rule of thumbs for gasifier selection because prior to going for the detailed design engineering, if there is any rule of thumb that we can opt for to screen some sort of potential gasifier or for our application. And then we'll discuss the detailed parameters for gasifier selection. Now, as I said that for gasifier, the most important parameter is the kind of feed that we use, and that we'll discuss. In the previous week also you saw that biomass feed itself is a very big challenge and that helps us to decide what kind of gasifier stove we should use. Similarly, at commercial scale gasifier also, biomass characterization becomes very important because it helps to determine the suitability for conversion. It also adds in reactor design. It helps in estimating the energy potential as well as it also helps us to predict the emissions and the environmental impact of the process. Now the major characterization tools and parameters that we use, eventually the first thing is related to the feedstock, the properties like proximate and ultimate composition. Then we learn about the heating value calculations, thermogravimetric behavior, and biochemical as well as the ash content. These are very important parameters which help us to decide that what kind of gasifier is suitable for what kind of feedstock. Particularly the um, thermal behavior and the composition, elemental composition as well as the biochemical composition as well. And the ash content we already saw that if there is high ash more than 20%, we need a ash pit and ash scraper, whereas for less than 20% ash content, the frequency of the ash removal may be lower and that will eventually lead to the less time consuming process. So this is something we'll be discussing in this course. So to begin with, the first parameter that we calculate for biomass is the proximate analysis. Now proximate analysis usually is done to calculate the moisture, volatile matter, ash content and the fixed carbon. And this is usually done in a oven. So typically if you see for moisture content, the prescribed ASTM standard, like I discussed in one of the lectures earlier, I think in week 3, the different codes for testing, but we didn't discuss the procedure. So if you see as per ASTM E871, we dry the biomass sample at 105 degrees Celsius until the constant weight is achieved. And then once the constant weight is achieved, what we do, we take the weight of the wet biomass and subtract the weight of the dry biomass divided by weight of the wet biomass and multiply by 100 to get percent. For example, let's say I have 10 gram wet biomass and after drying at 105 degrees Celsius and until the weight becomes the constant, I get 8.5 gram. That means what I'll do if I calculate moisture percent here, so it would be 10 minus 8.5 divided by 10 into 100. So that would eventually come approx 15%. So we can say that this is the 15% moisture content here. So similarly, the other property that we measure is the volatile matter. Now volatile matter is very important because that defines the tar formation as well as the flaring possibilities in the biomass. Now for this we follow the ASTM E872 code, wherein this is a furnace. So you see the moisture content, let's say we put the biomass, we heat it at 105 degrees Celsius. It is connected with the weighing balance and until the weight becomes constant, and we do that. After that, if we have to measure the volatile matter, we will increase the temperature to 950 degrees Celsius for 7 minutes without air in the same setup. So this is a furnace. You have this crucible where you put the sample, and this is the weighing balance with which this crucible is connected. So initially it will measure the weight and then you give temperature, and at 105 degrees Celsius you measure the weight and you can calculate the moisture content. Similarly, if I increase the temperature to 950 degrees Celsius in the absence of air, then what I will get is the volatile matter content. Now volatile matter, as I said, is crucial because it helps us to analyze that what kind of possible syngas composition we will get, whether it will be full of tar or it will be full of it will be a clean syngas, or end product may undergo flaring, or what kind of eventually the behavior of biomass will be during the reduction in the combustion zones in the gasifier. Similarly, to measure the ash content, what we do is we put the biomass here, the sample biomass here, and then we burn it at 750 degrees Celsius in air till the weight becomes constant. Now once the weight becomes constant, we know that it has whatever is left over is the ash. Okay, so we get the ash by measuring. Again, the method is same. If you have to find the ash percentage, you can take the initial weight minus the final weight divided by the initial weight, you will get the ash content percentage. Okay, now similarly the fixed carbon, the best way that once we know the moisture content, once we know the volatile matter, once we know the ash content, we can calculate the fixed carbon percent as 100 minus whatever is the moisture content plus volatile matter plus ash content. If we subtract them combinedly from the total biomass, we will get the fixed carbon. Or if we are calculating in percentage, then if we subtract the summation of moisture content, volatile matter and ash from the 100, then we will get the fixed carbon percent. Now this helps us to decide that what kind of gasifier may be suitable. For example, if we have high volatile material, it is ideal for gasification. Okay, if we have high ash content, there is a risk of slagging and falling, so we have to make provision for the continuous ash removal from the gasifying unit. Similarly, if it has low moisture, the combustion will be more efficient because less latent heat will be acquired by the water to convert into the water vapors. So here low moisture means more efficient. Similarly, we can measure the calorific value, okay, or we can measure the what is the elemental composition. So let's say once we are done with this ultimate the moisture content, the volatile matter, ash content and fixed carbon, we also want to know that my biomass consists of what is the, so fixed carbon we get here, but overall what is the carbon, what is the hydrogen, what is the nitrogen, what is the sulfur, and what is the oxygen. We know typically biomass contains carbon, hydrogen, and oxygen, and some sort of a minor amount of nitrogen and sulfur as well. So this, if we have to know this, we have to do elemental analysis, which is called as ultimate analysis, or in layman language we also call CHNSO, where we use the ASTM D5373 standard. The typical purpose is to determine the carbon, hydrogen, nitrogen, and sulfur using the CHNS analyzer. Oxygen, either we can put a oxygen analyzer as well, or we can calculate it by difference. So we can calculate it by difference. So once we found carbon, once we find hydrogen, nitrogen, sulfur weight percent, and then we know the ash content. Oxygen is 100 minus the summation of the carbon weight, hydrogen weight, nitrogen weight, sulfur weight, and ash. So we will get the oxygen content by doing this. Now this is a typical instrument for the elemental CHNS analyzer. Similarly, there are several companies that makes. The principle is very different. Okay, it's based on the combustion and the heating values. But the best part is once we know the elemental composition. For example, here you see one biomass has been tested which has 48% carbon, 6.2% hydrogen, 1.1% nitrogen, 0.5% sulfur, and 0% ash. So if I have to find the oxygen, what I will do, I will make O equals to 100 minus summation of 48.3 plus 1.6.2 plus 1.1 plus 0.5, and what I plus 0 for ash. Yeah. So 0.5 plus 0.0 the ash content. So this is carbon, this is hydrogen, this is nitrogen, this is sulfur, this is ash. If we subtract them combinedly from the 100%, we will get oxygen as 43.9% tentatively. Now, if we know the elemental composition, we can also use the Dulong equation to calculate. Okay. So this is very important. If we know how much carbon, how much hydrogen is there, we can know what kind of combustion behavior it will show. And we can tentatively estimate what kind of potential syngas composition we can get from it. It also helps us in estimating the emission and the efficiency. Of course, the more hydrogen and carbon we have, the more syngas we will be getting, the more volatile material we have, the more clean gas we will be getting. So that kind of decision we can make, particularly for elemental analysis. We can use it for the combustion modeling as well as to estimate the emissions and the efficiency. And also it is needed to calculate the calorific value, HHV, and both higher heating value and the lower heating value. Usually we use Dulong equation in this regard, that where we take all these the calorific values of carbon, hydrogen, nitrogen, sulfur all together, and then we measure what will be the combined calorific value of the overall process. Okay, so after the measurement of the ultimate analysis, the elemental composition of biomass, and the proximate analysis, we have already learned how to do that. What is the most important parameter is how to measure the LHV and HHV. So as I told you, to measure the LHV and HHV, we need a bomb calorimeter. So here, this is a bomb calorimeter. This is ignition wire, and this is, oh, you can correct it, this is vessel. Okay. So we follow ASTM D5865 method to measure the higher heating value of the biomass. In this method, what we do, we use a bomb calorimeter. We charge the biomass sample here. There is a combustion vessel and it is filled with the water outside, and then whatever biomass after combustion produces the heat, the water gets heated, and after water get heated, this is a thermometer which measures the temperature, and water is continuously stirred. So there is a uniform heat transfer. Now this thermometer shows that there will be, let's say, initial temperature, there will be a final temperature. So it will show a change in the temperature. because the biomass after combustion releases energy, you know that. So whatever energy will be produced by this will be transferred to this water, and then we can measure the delta T, and we can find out that how much heat is gained by the water. Okay, so the simple equation that we use here in this equation for measuring the energy content including the condensation of water vapor will depend on this. Okay, now if you look at in higher heating value, we are also measuring the energy content including the condensation of water vapor, which may not be accurate description. The reason is the water vapor we have to remove, and once we remove the water vapor, so we find out the lower heating value. So lower heating value is higher heating value minus, so this HHB, you can say HHB is higher heating value, and LHV is lower heating value. Okay, now if I subtract the latent heat of vaporization from the higher heating value, I'll get the lower heating value. Okay, now to do this, the equation that we use is the LHV equals to HHV minus 21.96 multiplied by H. Now this H we get from the ultimate analysis, that is the hydrogen percent. If you remember CHNSO, so this H comes from the ultimate analysis, and this 21.96 is an estimate of the energy lost as latent heat for each unit mass percent of hydrogen. Okay, so by using this equation, we can easily calculate that what is the lower heating value of the biomass. Okay, now the question is, how do we calculate higher heating value? Okay, so higher heating value, as I said here, when the biomass will go under combustion, it will release some energy. Okay, so if total biomass is went combustion and their complete combustion has happened, it will release some energy, and that energy will be transferred to the water. So if I can know how much energy is gained by water, I can tell how much energy is released by the biomass, right? Now when I can tell this how much energy is released, that actually is the energy of the biomass that we have kept as a sample in the bomb calorimeter. Okay, so for this the equation that we use is like here, you can say the HHV is mass of water which is getting heated, the specific heat capacity, and the temperature difference, because when water gains the energy, there will be a temperature difference. Okay, so we will see the temperature, and that is divided by the mass of the biomass that we have kept here as a sample. So this gives us the higher heating value. Okay, now the other way, as I told during the ultimate analysis, we can use the Dulong formula that is based on the elemental analysis, where the higher heating value in megajoule per kg is measured at 0.338 C plus 1.428 into H minus oxygen by 8 plus 0.095 S. Okay. Now this also gives us the heating value, higher heating value of the biomass. Okay, now as I was saying, once you get the HHV, if you subtract 21.96 into hydrogen from this, you will get LHV. So let's take one example. Let's say we have a biomass where we have HHV equals to 20 megajoule per kg and hydrogen content as 6%. So I can find, and this factor 21.96, so I can find LHV equals to 20 minus 21.96 into 0.06. This is the hydrogen percent. Okay, what I'll get around 18.68 megajoule per kg the biomass. You can see the example, it is more clearly illustrated here. It is more clearly illustrated here. So we have HHV of a biomass 20 megajoule per kg, hydrogen content as 6%. So what we do? We take the HHV 20 minus 21.96 multiplied by the hydrogen content in the fraction form 0.06, and what you get eventually is 18.68 megajoule per kg. So this is how you measure the calorific value or the higher heating value of the biomass sample, and that actually will help us to decide that whether this biomass is suitable for gasification or not. Besides that, we also have to understand the thermogravimetric behavior of the biomass. So we know that biomass has moisture. So biomass typically has moisture, and then we have volatile matter, cellulose, hemicellulose, and lignin, and these has different degradation temperature. And in gasification, there is first what happens in gasification, if you remember, what happens is drying, then pyrolysis, then oxidation, and then reduction. Okay, now we have to know this pyrolysis will happen at what temperature, because we have cellulose, we have hemicellulose, cellulose, and lignin, and all cannot degrade at the same temperature. Therefore, to decide the gasification temperature, it is very important that we should know this is not dry, this is drying. Okay, you please correct it, it is drying. Okay, so to know exactly what should be the thermal degradation temperature and what should be the gasification temperature, the thermogravimetric analysis of the biomass also becomes very important. So herein, how do we measure the thermogravimetric properties is like we use TGA, thermogravimetric analysis, as per the ASTM E1131 code. Now in this, what we do, we keep the sample and start increasing the temperature. So when the temperature will increase, initially the moisture will get removed, then pyrolysis will happen, the hemicellulose will start breaking. This is from the experience and from the earlier research. You can say the hemicellulose breaks at lower temperature. So hemicellulose will break, then cellulose will break, then lignin will break. Okay, so this we can see TGA measures the mass loss with respect to temperature increase. Okay, usually it is carried out under inert or oxidative atmosphere depending on what we want to know. Usually at less than 150 degrees Celsius temperature, we can see the moisture loss. From 150 to 500 degrees Celsius, we can see the volatile release, and above 500 degrees Celsius, we can see the char decomposition. Now we can also use the DTG curve to determine the reaction rates. Okay, and also it helps us to identify the degradation stages. Okay, and also to study the stability and kinetics. For example, I can use the thermal degradation as conversion and use this equation to find the activation energy for all kind of calculations for the biomass. Okay, then we have lignocellulosic biomass composition. As I said in the beginning, that lignocellulosic biomass particularly has lignin, cellulose, and hemicellulose, and some hollow cellulose, that are the polymers. Okay, so if we have to know exact structure of cellulose, hemicellulose, lignin is yet to be defined. So what happens that we have to find some indirect methods to calculate how much cellulose or hemicellulose is there. Typically from the experience, it is from the research earlier, it is said that the lignocellulosic biomass typically contains 40 to 50% crystalline glucose, whereas the hemicellulose content is around 20 to 35%, which is a amorphous polysaccharide. Okay, similarly lignin, which is a polyaromatic, has content around 10 to 30%. In I think week 3 lectures, I already said that lignin acts as a binder, and it's a polyaromatic, you can say, which after the depolymerization becomes the aromatic. So it acts as a binder in the biomass. Now, how do we measure? That is the question. So as of now, there is no standard instrument that measures directly cellulose or that measures directly lignin. What we do, we use the biochemical characterization method. For example, NREL or TP 510-42618. In this method, what we do two-step acid hydrolysis. Okay, and the tools that we use are HPLC for analysis of the compounds that we get after the hydrolysis, FTR for analysis of the functional group, and then NMRADF or NDF for fiber composition. Okay. For example, enzymatic hydrolysis we can use, that's why it is called biochemical. And now we also use the chemical hydrolysis as well to measure the glucose content. And once we know the glucose content, we can also know the cellulose content in the biomass. For example, the wheat straw, which is enzymatically saccharified, it yields around 82% glucose yield. Okay, so we know that how much glucose will be there because their decomposition temperature varies. Like I said, this is easy to degrade, this is moderate, this is tough. So now depending on which component is more, the gasification behavior will change because their degradation temperature is different. Therefore, the efficiency of the gasification is influenced by the cellulose to lignin ratio. More lignin, more requirement of high temperature. Less lignin, less requirement of higher temperature. Okay. For example, it is preferable to have low lignin biomass, but then we can't change the biomass composition. We can only choose from the available biomass sources. In order to analyze the lignin content, we use Classen method. Like here I showed you that we use two-step acid hydrolysis method or biochemical method to measure the lignocellulosic biomass composition. Similarly, for lignin analysis, we use Classen method where the insoluble fraction is measured after the acid digestion. Okay, and the soluble lignin is measured by UV at 280 nanometers. NMR and FTR are used for the functional group identification present in the lignin. The conversion relevance, if you see, is very important because it tells us that what kind of product we get from where. For example, cellulose can give me glucose and ethanol. Hemicellulose can give me xylose and furfural. Lignin can give me biochar. But if I talk in terms of gasification, this is easiest to gasify. This is moderate to gasify. This is elevated temperature, I can say. Elevated temperature. It requires elevated temperature. Okay. Or I can say tough to gasify. Okay. So for gasification, this is very important that we should know the composition of the lignocellulosic biomass as well. Then the ash content, definitely it is very important. As I said, the ash can lead to the clinkering and slagging, and then depending on how much is the ash content, we need to put ash removal system. So the ash is characterized using the ASTM D3682 method or D4326 method. XRF is one of the major instruments that is used to detect the major and minor elements present in the biomass. Similarly, we can use ICP OES, AS for trace metal quantification. We can also use ICP MS for trace metal classification or quantification. Similarly, we use scanning electron microscopy and ADS to study the morphology and surface analysis of the biomass sample. Okay. We also study the ash fusion temperature according to the ASTM D1857 code to know the softening and melting temperature of the biomass. Now, why we are concerned about ash content, I told you several times that the ash leads to clinkering and slagging. And the major elements which are present here, you can see These are alkaline earth metals like potassium, sodium, calcium, magnesium, and silica. Now, the high silica content is there, it will lead to slagging. Okay. Then we have to do acid leaching, washing, etc. in order to get rid of this ash. Okay. Similarly, we can measure the physical properties that includes the bulk density, which is measured as per the ASTM code E873. We need to measure the particle size because that will change the fluidization behavior. Density as well also. This changes the flow properties of the biomass. So particle size also is a very important property, especially if we are using the fluidized bed gasifiers, then that becomes very important. So the particle size classification is done as per the ASTM D1921 method, where we use different types of sieves to categorize the particles into different sizes. We also need to measure the surface area for porosity and adsorption. For gasification, it may not be needed. However, for other applications, it may be needed. Besides that, the thermal properties measurement, for example, a specific heat which is measured as per ASTM E1269, which is measured by the DSC. Again, DSC is a part of TGA. So usually we see that TGA, DDA, DSC comes together in an instrument or maybe separately. We also need to measure the thermal conductivity as per the ASTM code E1461 for transient plane source method. Okay. The impact, I mean, this overall impacts the reactor heat transfer efficiency as well as the particle size. This affects the fluidization or the flowability of the biomass. The thermal properties affects the heat transfer efficiency in a reactor. If I talk about the further impact, the rises like if you see high ash content, so it requires slag control. If it has low ash, high volatile, there will be efficient combustion. If we are using algae which doesn't have lignin, so this kind of biomass will be suitable for hydrothermal liquefaction. Wood chips which has high lignin, better for pyrolysis and bioil production. So these are the impact. I'm telling you why characterization is important for gasification and for other processing part. Similarly, the characteristics or the properties of the biomass have an impact on reactor design. For example, if there is moisture, you need a pre-drying. The particle size affects the flow and residence time. The ash content influences the material selection and maintenance because many of these elements are corrosive as per the ash content. So this is all for today's class. See you in the next class. Thank you.